Hey loyal fans, this video is about SolveSpace, a free open source drawing program you can use to design three-dimensional solid models for animation and 3D printing. Even though SolveSpace is a powerful design program, it'll run on a Raspberry Pi 5, this itty-bitty computer right here. I've made other SolveSpace tutorials, links in the description, but I recommend that you watch this one first. The skills you acquire learning SolveSpace are transferable to other computer design programs as well as to your general computer knowledge, so time well spent. In this video, I introduce SolveSpace and cover the basics. But first, let me give you some background about YouTube and the future of employment. Over my decade of making and watching YouTube videos, I've noticed a big change. Most video creators now embed advertisements in their videos. So, YouTube shows you their ads, then creators show you theirs. As a result, YouTube is becoming more like television, a vast commercial wasteland. But I'm not here to make a fortune. I'm here to make a difference. My payoff is that people learn stuff from my videos. That's all. And for me, that's enough. So when you like and subscribe to my channel, which I hope you will, you're casting a vote for free, non-commercial, educational content. On the topic of employment, much has been said about AI and automation, how robots will take over many jobs. That seems likely, but there is a remedy. The workforce of the future will consist of a small group of people who tell robots what to do, then robots tell everyone else what to do. The remedy is to become a member of the robot instructor group. You do this by learning about computers, figuring out how they think. This video is part of that process. So hey, let's get started. Okay, now for installation. SolveSpace is free and open source, and it has installers for Windows, Linux, and Macintosh. On Windows or Macintosh, just run a browser and enter a search string of SolveSpace. Quickly going through the... Eventually you'll get to this page. And the Windows choices are this one, SolveSpace Exec, and this one, OpenMP Exec, which gives you the advantage of exploiting multiple cores if your computer has multiple cores. And the DMG choice is for a Macintosh, which I can't cover. I don't have a Macintosh. But let me go ahead and download one of these just to see what happens. Now I already have one, so that didn't take long. Okay, now I'm not going to reinstall SolveSpace, but just go to your downloads directory and find SolveSpace and click it, and you can go through the install process. That pretty much does it for Windows. On Linux, things are much simpler. Open a terminal and become root. And first thing I want you to do is update the archive, the local archive, this way. And once the archive has been updated, you can simply enter these instructions will work for many of the Linux distributions that are based on Debian. There are some other distributions that you'll have to sort out for yourself, I'm sorry to say. I can only vouch for how it works on Debian and Debian derivatives like Ubuntu and others. Anyway, this is the instruction to install SolveSpace. Notice how much easier this is than Windows. And of course, I already have it installed, so that will work for you. It won't work here. And one more thing. Different distributions of Linux have different versions of SolveSpace available. So you may notice some small differences between the tutorials coming up on this video and your own experience, but they should be minor. Well, that should do it for install. SolveSpace is a modern version of a drawing tablet with an important difference. It lets you draw in 3 dimensions. Imagine a paper drawing tablet like this, one that lets you draw something you want to build. Now imagine drawing in 3 dimensions, not just 2. Wouldn't that be useful? But this is now part of reality. SolveSpace lets you draw in 3 dimensions. In the 3D SolveSpace universe, we identify space dimensions with letters and colors. The letter X refers to the left-right dimension and is red. The letter Y moves far and near and is green. The third dimension, identified by a blue Z, ascends vertically from the page. Try to imagine a city where the X dimension is east-west, Y is north-south, and Z is up. Become familiar with these 3 dimensions, their letters and colors. I ask this because SolveSpace and other drawing programs use them, graphics programs like Blender use them, and 3D printers use them, so they help you stay oriented as you move from one program and activity to another. I'd like you to become comfortable with a 3-dimensional drawing space. Computer drawing has 2 key phases. First, you make a 2-dimensional sketch. Then you expand it into 3 dimensions in a process called extrusion. I strongly encourage you to experiment with SolveSpace. Try things out before starting serious projects so you know how to recover from errors before committing yourself to a large project where errors might be more important. Think about where your new SolveSpace skills might take you. After you build a 3D model, you can export it to a computer graphics program like Blender and animate it. You can also 3D print your model, turn it into something real and useful. By the way, you can print your models without owning a 3D printer. Many public libraries now have 3D printers available at a very reasonable cost, sometimes free, so you can turn your creations into real objects. Imagine inventing a machine, a gadget, or a work of art, then making it real at your local library. In the next part of this video, I show how to create 3D drawings, then export them into reality. Because this is a primer, a beginner's guide, I'll show the basics of 2D drawing, nothing complicated. I have more advanced videos, links in the description. If I miss something, please leave a comment and I'll cover it in a future video. Notice the keyboard display in the upper left. If I press keys, let's see, what key can I press without messing everything up? They show up there so you can follow what keys I'm pressing using that. The property browser is important to have on the screen. It's in a separate window. If it doesn't show up when you run SolveSpace, press the Tab key and that will make it appear. And then slide it over to the right to get it out of the way of the editing area. The taskbar, this gadget here, has 3 main sections. The top section is drawing commands. The middle section are constraints, which I'll explain what constraints are in a bit. And the bottom section is mostly extrusion commands. extrusion commands are used to turn a 2D sketch into a 3D object. So let's just get started. I'll just draw some lines. Press S for start a line drawing. And I'm going to deliberately leave a gap in my drawing to show the fact that a SolveSpace drawing must be a closed contour. It must be a closed shape, which this one is not. So there's immediately an error here and an error indication here on the property browser. So to solve this one, I'm going to select the two endpoints and press O for join or origin. I have an extra line segment in there which I didn't want. That's something that the line drawing algorithm sometimes does. It shows a it has an extra line that doesn't even show up. Okay, now I deliberately just drew some lines, random lines, and in this column here in the property browser is the word DOF, which stands for degrees of freedom. And there are 8 degrees of freedom right now in my drawing. A degree of freedom is a fancy way of saying something that has not been defined. So I'm going to start, what that means, by the way, is that there are no constraints. The drawing is out of control. It doesn't have anything defined. So I'm going to start by selecting this line and pressing V for vertical. Now that forces that line to be vertical, and it's defined as a vertical line. So that takes care of one of the degrees of freedom. I'll do the same thing over here. Now there's 6 degrees of freedom. Now in this case, I'm going to press H for horizontal. Now there's 5 degrees of freedom. And now let me just make this a bit larger. And I still have 4 degrees of freedom. And a degree of freedom is an undefined line length or line orientation or a line's position in space and a handful of others. But basically the idea is it's something that's undefined in the drawing. So first let's select this line and give it a length. I'm going to say that it's 100 millimeters long. Now you see we have 1 less degree of freedom. And this one, I'm going to say the same, 100. Now, there's only 2 degrees of freedom left, and this square is pretty well defined in every respect except for where it's located in space. So to solve that problem, I'm going to select these 2 points and the vertical line axis point of the drawing and say symmetrical, Y for symmetrical. And now the entire drawing surface is red, and it says that I have redundant constraints. In other words, I have one more specifier than is needed to fully define the drawing, or a particular part of the drawing. So I'm going to eliminate that one. And I'm going to do the same thing. I'm going to specify this line as being symmetrical about the horizontal. Same idea. And again, I have a redundant constraint, which I'll remove. Now I have a drawing that is fully constrained, and it just says, okay. I actually would have preferred it if they had had a 0 in both of these locations. Whatever. So at this point, I'm going to leap forward from constraints down to extrusion commands. First I'm going to make this, I'm going to rotate this around so you can see what's going on. Now I have selected the drawing I just created, and I'm going to apply this particular extrusion command, which extrudes my 2-dimensional drawing into 3-dimensional space. And I have the choice of having my drawing be one-sided, which is only on one side of the drawing plane that the original 2D drawing was created on, or two-sided. So I'm going to choose two-sided for my next little demo here, and make this a little less steep. Now, according to this extrusion, which has appeared in the property list, the first drawing is here, and that's in sketch in plane. And the extrusion I created has its own entry called extrude. And I think I'll change its color to red for a reason I'll explain in a bit. And I still have 1 degree of freedom. And the reason I have 1 degree of freedom is I haven't specified the depth of the extrusion. So I'll do that now. I'll see 84, I'm going to be 50. Okay, now we have no degrees of freedom. Now I'm going to create a new drawing in the same plane by selecting that plane, the XY plane, and pressing Shift W, which is a command to create a new drawing. And I'm going to create a circle, which isn't visible yet. Make it visible here. Now, this is the new drawing, and I'm going to make another extrusion, but I'm going to change its color to blue so I won't get confused. And I'm going to make it two-sided like the other one. Okay, so basically I have 2 drawings and 2 extrusions, the red extrusion and the blue extrusion. And they're laid over on top of each other at the moment. But for fun, I'm going to make all the drawing lines invisible. And what we're seeing is the union of the 2 objects, the red and the blue object. If instead I select difference, we'll see how they differ, which is that part of the square of the rectangle outside the cylinder is the only part that differs between the 2. And now if I select intersection, all that displays are the parts of the 2 drawings, that the 2 extrusions that intersect in 3 space. So this is a union of the 2 objects, which is everything. This is the difference, the parts that aren't overlapping. And this is the intersection, the parts that are overlapping between the 2 objects. Now, just for the fun of it, I'm going to save this object I've drawn. And I think I'll save it as a wavefront object, which I've saved before under that same name. Very important at this point, I've saved the result of this drawing session. But what I haven't saved is the SolveSpace file that defines the commands. So I want to do that. Let's say save as. This is very important. Notice how I just saved 2 different files. I saved a file containing the SolveSpace information to be able to do this drawing again. And I also saved the outcome of the drawing, this object, separately. And they appeared separately in the listing of the program. Now, just to get ahead of myself a little bit here, I'm going to try importing this drawing into Blender, which I had imported it before. Here we go, importing into Blender. Now, it pretty much looks the same. Blender has a bunch of advantages over SolveSpace for viewing objects that I've created. Okay, that's looked easy enough. I simply took the file. Let me do that again to make sure that it was clear what happened. So I have an empty Blender session, and I grab the file from the File Explorer, and I drag it onto the Blender program and confirm that that's what I want to do, and it accepted it. In the same way, I'm going to run Prusa Slicer, which is a slicer program for 3D printing, and I'm going to, wait a minute, I'm going to also save this in a way more suitable for 3D printing. I want a STL. Now, I have the STL here on my list. I'm going to drag it into Prusa Slicer, and the orientation of an object that's imported into either Blender or Prusa Slicer or another slicer program is important. That's an advanced topic, because in SolveSpace, which orientation an object has when it's exported depends on on what plane it's drawn. I happen to have drawn on the XY plane, which means the Z-axis is pointed outward, which is consistent with what we saw in Prusa Slicer, because the Z-axis in Prusa Slicer is vertical. So that's consistent. So that's something that is important to plan for if you're drawing an object and you want to conveniently get it into a 3D printing slicer program like Prusa Slicer. You'll want to make sure you draw on the correct plane. I'd like to go through a few advanced SolveSpace features and actions, starting with drawing planes. SolveSpace offers 3 default drawing planes, visible right now. I'll touch each one of them. You make your choice by first rotating the editing area in 3 space to make the planes visible, as I've just done. Looks better in perspective. And then you select one by pressing Shift W, like that. I'm just going to go through a few examples. The drawing plane choice is important when you're preparing a model for 3D printing, where the model's orientation is important. The choice of plane depends on the drawing strategy, and direct experience is the best teacher. Here's an example to make my point. Here's a cup drawing. Here's the original drawing. And here's the end result. And let's say that I've designed this cup without really paying any attention to which drawing plane I'm using. And then I decide to submit my cup to a 3D printer slicer program. Whoops. What I discover now is that it really didn't matter in SolveSpace, because all the planes are equivalent mathematically. But the orientation matters later. The solution is to plan out your drawings in such a way that you have the right plane to draw on to get the desired result after export. Exporting into Blender has the same issue. You can see what the problem is. Everywhere you go with the export, if you've chosen the wrong plane to begin with, you'll regret it for a long time afterwards. It's better off to plan ahead and choose the correct plane to begin with. I should add that even though there are 3 default planes in SolveSpace, an experienced user can create any number of additional drawing planes with proper techniques. any position and orientation. This is about reference dimensions, where you can define a dimension, a size, in one drawing, and then use it elsewhere. You can export dimensions from one drawing to another. Let me start by creating a line and make it a construction with a dimension of 125 millimeters. Now, let's extend it into 2 dimensions in the same drawing, as so. Make that a construction line. Now those are equal. See the equal marks. If I check this line, it has a reference. It's a reference to this one's dimension. Now I can extend this to a 3rd dimension by starting a drawing in a new dimension, a new plane, excuse me. And make these share a dimension. Now in all 3 dimensions, I have a reference to the original. Okay. Now, finally, since we have all these reference dimensions, I'll create yet another drawing. And in this drawing, I'll create a square that relies on the reference dimensions. And let's pin this to the same here. Now we have a square that is defined by the original reference, as you can see. Now one more step. Let me extrude this cube . And let's see, let's get a hold of our, now this line right here is the reference dimension that I want to use. And this is the surface that I want to force into that dimension. Now if I simply try to make them equivalent, I can't do that, it turns out, because of a bug in SolveSpace. So instead of doing it that way, I'll create a tiny dimension, a tiny size that forces all 3 sides of the cube to be equivalent. Now, this cube is entirely defined by the reference dimension that I defined earlier. All these dimensions of the cube are twice the size of the radius that I defined in the original drawing. Here's the original drawing. And the final result, cube, which has sides that are twice the size of the reference dimension. Now, what this meant to demonstrate is that you can have a drawing. Oh, let me try something. I hadn't thought of this. Let me try this 130. Now I've just changed the reference dimension, and all the resulting dimensions cooperated by changing. Let's do a little more dramatic. Let's try a 200 and So this cube that I've created is completely reliant in 3 dimensions on this single line, this one right here, in the original reference drawing. So this is a way to create and export sizes from one drawing to another and throughout a project. This is a fairly practical, somewhat advanced drawing project that creates a threaded bolt. It's meant to show what SolveSpace can do, as well as create an example of a project with real-world applications. Okay, we want this to be this is a particular size because I want this project to work with actual hardware. So I have to pay particular attention to dimensions. Now we're going to make a hexagon. It doesn't really matter how carefully one draws these line segments because they're all going to be forced to be equal in a sec. Not every SolveSpace version can do this trick. I just forced them all to be identical with one keystroke. Some SolveSpace versions, it may be necessary to select pairs of sides and make them equivalent, pair by pair. But this version I'm running is the latest version, and I can get away with that trick. Okay, there's the bolt head. Now, let's just go over here and start a new drawing. Once again, a particular dimension is required. And there's the bolt shaft. And a new drawing. Now, we're going to create the thread. And we want it to be nearly touching the shaft, but not quite. In the same way, it has to be nearly touching this bottom dimension. Okay, now we're ready for creating a helix, a somewhat more exotic operation. And we're going to define the thread pitch of 1.5 millimeters per turn. And we're going to position it correctly. Now, let's momentarily take a look at what we've created. This is a very crude bolt at this point. It's by no means complete. The next step I take really makes all the difference. And so first, a new drawing. It's not obvious what this part does, but it will become obvious soon. And I forgot to do that. Now, I've created this funny looking object, which won't work unless I make it intersect with the remainder of the bolt, which I've just done. Now, let me just see, hide all. And ta-da, we have essentially a finished bolt. And it is a bolt that will fit with regular standard hardware because of certain dimensions that I specified as I created it. When creating these tutorials, it occurs to me I may dwell too long on something everybody knows, but miss something that needs more exposition. So if I missed anything, please tell me in the comments and I'll catch it in the next video. This tutorial's XYZ number system is an example of Cartesian coordinates, named after René Descartes, a 17th century mathematician who greatly simplified the lives of people who think about space and time. I should explain that Cartesian coordinates are part of math. Designing 3D models is too. Actually, all of science and engineering are part of math. In fact, I'm going to tell you a secret. Everything is part of math. I know this might sound like a street corner preacher trying to save you from whatever, but I will say this, if you don't learn math, you'll be perpetually lied to by people who know more math than you do. Here are some of the lies math illiterates get told. False belief number 1. When flipping a coin, each tails outcome increases the chance for a heads outcome on the next flip. So a series of tails outcomes greatly increases the chance for a heads outcome. This is called the gambler's fallacy, and it's false. In fact, regardless of prior outcomes, a new coin flip will fall equally heads or tails. If a coin comes up tails 10 times in a row, the next coin flip's probability is, wait for it, 50% heads, 50% tails, forever, toujours, sans cesse. This doesn't mean coins don't show amazing runs of all heads or tails. It only means past events can't be used to predict the next event. Casinos know this, but gamblers don't. Casinos are rich, but a typical gambler is in debt. False belief number 2. Lotteries are a good way to get rich. Totally false. Please think about this. If there was a reasonable chance to get rich buying lottery tickets, lotteries would collapse. But lotteries make huge amounts of money from math illiterates. Here are the numbers for my home state's lottery on the day I write this. In my state's lottery, a ticket costs $2. The jackpot is $13.8 million if you cash out, which is the recommended action. The probability to win is 1 in 292 million. This means to have a 50% chance to win, you must buy 292 million $2 lottery tickets, total cost $584 million, against a prize of $31.8 million, or an expected loss of $552 million and change if you win. Another way to say this is your chance to be killed by lightning is 19,000 times greater than winning the lottery. Also, even if you win, the chance this will make you happy is vanishingly small. There are any number of sad stories of people who won the lottery, then suffered one catastrophe after another, such that they wish it hadn't happened at all. But these people aren't the brightest bears in the woods. How do we know this? They buy lottery tickets. How smart can they be? Well, enough about math illiterates for now. Maybe I'll create a math illiteracy video with more examples. If you'd like to see one, tell me in the comments. Hey, thanks for watching. Gotta go.